All right, CalcAB, I'm here today to tell you about the fundamental theorem of calculus, also known as the FTC. Okay, now I'll have a motivational quote in class, but as you can imagine by the name, the fundamental theorem is something that is crucially important to this. And what this basically does is it connects two ideas that you probably suspected were similar. It connects antiderivatives, so the opposite of a derivative, to definite integrals, which of course we do as area under a curve. So it shows that there is indeed a relationship between finding the area under a curve with doing the opposite of a derivative. So without further ado, here's what this tells us. This tells us that if big F, well, let's back up a step. If your function is continuous and big F is an antiderivative, using the same thing, meaning you integrate little f, you get big F. Then, if you take the definite integral from a to b of f of x dx, that gives you big F of b minus big F of a. Wow. So first off, let's think about this, because this is truly remarkable. Because this is saying this is just an area under a curve. So if you have some weird function and you need to find the area under the curve, this is saying all you have to do is take the antiderivative and then just plug in 2 points. Plug in the top minus plug in whatever you get for the bottom. And this is remarkable, and this is really going to be central for everything else we do in this class. If you want to find the area under a curve, all you have to do is take the antiderivative and plug in 2 points. Incredible. Incredible. So let's look at some examples, talk about what this means. So let's suppose you have to find the area under the curve from 1 to 2 of x squared. Now this is something that I think could be pretty challenging, right? Like we know what the graph looks like, but if we wanted to do this geometrically, like finding the area from 1 to 2, that little sliver in there is not necessarily an easy problem. But what this is saying is that you could just find an antiderivative and then plug in. You just plug in the top bound, you plug in the bottom bound. Okay, so if we want to find this pink area from 1 to 2, all we have to do is take the antiderivative of x squared. So that's x cubed over 3. And then the way we do this is we write a little bar from 1 to 2. Basically, after you integrate, you get the bar. And that bar just means like evaluate at 2, evaluate at 1, and then you subtract. So you're going to plug in the 2, and then you'll plug in the 1, and then subtract. Okay, so when you plug in the 2, you get 2 cubed over 3. When you plug in the 1, you get 1 cubed over 3. So this is just me plugging in 1 and 2, the top and the bottom, into that. So anyway, I'll get 8 thirds minus 1/3, which equals 7 thirds. And again, what that 7 thirds means is that gives you the area of this pink shaded region there. Beautiful, right? Like we could just estimate this area with a Riemann sum before, but now we can actually find this area by just taking an antiderivative and just plugging in 2 points. Incredible. So that's what this bar means, just evaluate the 2 points and then subtract. Okay, now a couple other things here. You might be wondering why no plus c? What happened to the plus c from our antiderivative? And the answer to that is that it cancels. You don't have to, I mean, you can write it if you want, but you don't have to because it cancels every time. Because think about it, if you just get x cubed over 3 plus c, and you evaluate that whole thing from 1 to 2, so you plug in the 2, so you get 8 over 3 plus c. You plug in the 1, you get 1 over 3 plus c. So you just get 8 thirds plus c minus 1/3 minus c, and the c's cancel. So it just goes away. So that's why you don't need a plus c on this. Okay, let's go ahead and do some other examples. What if you had the integral from 0 to pi over 2 of sine of x dx? Now, you're all great students. You know what this looks like, right? Sine of x looks like that, and then goes down and so forth. So we're just trying to find the area from 0 to pi over 2. So that little weird curved region up to the first max at pi over 2. Okay, so first off, we think, what is the antiderivative of sine? Derivative of cosine is negative sine, so that'll be negative cosine of x, going from 0 to pi over 2. Okay, so what that's going to be is that's going to be negative cosine of pi over 2 minus negative cosine of 0. Now again, I'm a good student, so I remember the cosine of pi over 2 is at the top, so the cosine is 0. So it's 0 plus the cosine of 0, so 0 plus 1. Oh, beautiful. It's just 1. Great. So that means that weird curvy area worked out to just be exactly 1. Oh, what a nice problem. Okay, let's look at some other ones here. So let's suppose we have to find the integral 1 to 2 of x cubed minus 5. Okay, so let's go ahead and do this again in two different parts. So first off, we find my antiderivative, and then I plug in. And just do the top of my spot. So the antiderivative here is x to the 4 over 4 minus 5x, and then I plug in 1 to 2. When you have two terms, I like to put them both in parentheses to remind me just to plug all into the first and then minus plug all into the second. So I plug a 2, I get 2 to the 4 over 4 minus 5 times 2. Plug in 1, I get 1/4 minus 5 times 1. Okay, so what is that going to be? Well, this is going to be 16 over 4 minus 10, so it's going to be negative 6 minus 1/4 minus 5. Okay, so when I'll distribute that out, I'll get negative 6 minus 1/4 plus 5. So I'll get negative 1 minus 1/4, also known as negative 5 over 4. Okay, cool. So one thing worth noting, this is a negative, and if this is negative, don't freak out. That just means that there's more area under the axis. And that works out just automatically. You don't have to add anything negative yourself. But it's just saying like you have more area under the curve than we have above it, right? There's more area down there than above. That's all it means to have a negative. Okay, one thing for you to try here is let's try this one. So feel free to try this and pause it on your own. Let's try the integral from 2 to 1 of x cubed minus 5 dx. Now, hopefully you know the answer, right? If you switch the bounds from these two, you should just get the negative. So go ahead and pause and give that a try on your own. All right. Anyway, so here, same thing. We get x to the 4 minus 5x, same antiderivative, plug in 2 and 1. When you plug in 1, you get 1/4 minus 5. When you plug in 2, 2 to the 4th is 16 over 4 is 4 minus 10. So you get 1/4 minus 5 plus 6. So you get 1 plus 1/4 or positive 5/4. Oh, cool. Switching the bounds does just switch the sign. Nice. All right. Let's look at one more with a couple different parts and one that's going to be a little more complex. So let's say we have to find the antiderivative pi to 2 pi of 1 over x plus cosine of x minus 3. Again, I would suggest go ahead and hit the pause button right now. Try this on your own for a minute and write your answer out. Okay, well, we have three parts. 1 over x is the ln of absolute x. Derivative of sine is cosine, so integral of cosine is sine. And then minus a 3x. And then we go from pi to 2 pi. All right, so I have all three terms. So I'm going to plug the 2 pi into all three terms first. So I'm going to get ln of 2 pi plus sine of 2 pi minus 6 pi minus. And now I'll plug in the pi to each of the three. Okay, so I get ln of pi plus the sine of pi minus 3 pi. All right. Now, a lot of the cool kids in the class at this point have realized, okay, if you're at pi and at 2 pi, like this is 0, it's also 2 pi, that means that the sine of both of those is actually 0. That worked out really nicely. So this just becomes ln of 2 pi minus 6 pi minus ln of pi plus 3 pi. So we have ln of 2 pi minus the ln of pi minus 3 pi. Combine those. And then one of the cool tricks we've seen, right, is if you have two logs put together, if you have like ln of 2 pi minus ln of pi, you can turn that into ln of 2 pi over pi. That's the log rule, right? You can combine those. So you just make them ln of, and then the pi's cancel, ln of 2 minus 3 pi. Okay. Beautiful. So again, we're just finding areas under a curve. That's how you want to think about these. To find these areas under the curve just by taking an antiderivative and plugging in. This is a powerful strategy, and I think you guys are going to like these. All right, bring me some questions to class, and I'll see you guys soon.